Our third speaker will be Bailey Gu. Bailey will tell us about the benefits and costs of quantum error correction with erasure qubits.
Yeah, thanks for that introduction. I'm Bailey. I'm a postdoc at Yale. And today I'm going to be telling you about erasure qubits. So this was joint work with Yotam Vaknin, Alex Retzker, and Alex Kubica. So to get started, let me give you a very simple example of why we want to use erasure qubits. So here is the surface code. And let's suppose that the 3 qubits in the middle have been corrupted by some unknown Pauli error, let's say some Z error, which would give the syndrome in the highlighted squares. So if we don't know anything about these errors, we would try to apply the minimum weight correction, which would be to apply Z to these 2 qubits. But then we see that this actually causes a logical error. But instead, if these were erasure errors, we would have some flags telling us, like, OK, these are the only places where errors could have occurred. And if we know this extra information, then of course we would apply the corrections at the right locations, and that would take us back to the original code state. So in general, if we have erasure errors, we could correct d-1 erasure errors, whereas for unknown Pauli, we would only be able to do d-1/2. And for example, that would translate into a better logical error rate scaling. Another advantage of erasure errors is that we will get a higher threshold. So in the surface code, we can tolerate up to 50% erasure noise versus only 19% for depolarizing noise, even under optimal decoding. So to set the terminology then, an erasure qubit is going to be one where the dominant noise source is to actually take you out of the computational subspace into some erasure subspace, and you can do some detection to actually tell you that you have leaked out of the computational subspace. And this kind of erasure bias can be either native or engineered in some platforms. And actually, many platforms can support erasure conversion, like superconducting circuits, neutral atoms, trapped ions. OK, so now I've convinced you to use erasure qubits, so that's the end of my talk. Just kidding. OK, so as you can imagine, there's going to be some extra complications involved. And that's, OK, for the first one is, when we talk about erasure qubits, we actually need to have additional physical operations. Like the experimentalists need to have some way of actually implementing these erasure checks. And furthermore, the detection of erasures could be imperfect. We might have some false positive or false negative erasure detections. And in the process of performing erasure checks, this could actually cause more noise into the system. So these are all things that would degrade the performance of erasure qubits. And even to study erasure qubits, we need to develop some framework to actually simulate what's happening with the circuit and have some way of decoding circuits with erasure qubits. And at the end of the day, we want to have some way to fairly compare the performance of erasure qubits with that of standard qubits. So the main question that I want to address in this talk is, given all of these extra complications, are erasure qubits worth it? Should we go and use these erasure qubits? The outline of my talk. So first, I'll tell you about our formalism for working with erasure qubits. And this is a framework that's expressive enough to capture the key features of some realistic noise models affecting these erasure qubits, but it's also going to be simple enough that we can actually study it. I'll also talk about decoding erasure circuits. So I'll present a mapping of erasure circuits to standard stabilizer circuits that allows us to decode. And I'll also give some numerical results on simulations of the surface code and also floquet codes using this framework. And finally, I'll give some conclusions on what is the benefit of using erasure qubits. OK, good. So when we work with stabilizer circuits, we would specify different basic operations like state preparation or measurement in a Pauli basis. We have Clifford gates, so this is all very standard. But what we also include, when we're working with erasure qubits, we need to include extra operations. So one of them is going to be erasure checks. So we imagine that the erasure qubit is described by at least a 3-level system where we have the computational subspace and also an erasure subspace. And then this erasure check would perform a projective measurement telling us if the qubit has been erased or not. So this will be denoted by EC. So this is not error correction, it's erasure check. Then we also have some reset operation where if the qubit has been erased, then we should be able to reinitialize it into the computational subspace, for example, as the maximally mixed state. And so we need to explicitly specify in the circuit where to actually place the erasure checks and the reset operations. Okay, so now that we specified what we actually do in the circuit, we need to talk about what noise can affect the states. So we want to add noise in a standard way so that we can compare different circuits. And what we imagine doing is that we place erasure locations between consecutive operations. So this E is an erasure location. And at the erasure location, the qubit has some probability of decaying to the erasure subspace. Then we would also put polynoise after 2-qubit or 1-qubit operations. So this is the same as for stabilizer circuits. And we would also put bit flip noise on the classical outcomes. So the classical outcomes would be for erasure checks and also for some poly measurements. So far, this is pretty general. Like we can specify different noise strength at different locations. But for this talk, I'll mostly consider 3 parameters characterizing the noise. So one is the E, the erasure rate. So with the probability of being erased at each of the erasure locations. Then we also have P, some poly error rate. Let's say you saw some depolarizing channel. And Q would be the classical bit flip rate. Okay, there's actually one more ingredient that we need to specify when working with erasure circuits, and that's how erasure spreads through entangling operations. So if we're just dealing with stabilizer circuits, we know exactly how polynoise spreads through Clifford gates. We just do the conjugation. But for erasure, we need to explicitly specify, and this would maybe depend on the hardware. But we can imagine several scenarios, like if an unerased qubit interacts with an erased one, it could get depolarized, or maybe the spread would be to get dephased, or maybe itself would get erased. So all of these are possibilities. But for us, we would mostly consider the depolarizing case because it's kind of a worst case scenario. Like you just lose all information about the other qubit as well. So we consider depolarizing spread. Okay, so with this framework, we can talk about how to simulate these circuits. And what we need to do is use one classical bit per qubit to just keep track of the erasure information, whether or not you're erased. And this implicitly assumes that we cannot create like a superposition between erased and computational states. Then we can just keep track of the stabilizers as we progress through the circuit. And for the erased qubits, if we're performing like a poly measurement on erased qubits, then we would imagine just to randomize the outcome. And we would also apply the errors to other qubits that interact with erased qubits according to whatever rule we picked before. So all of this can be done numerically through software such as STIM. Okay, now let me get into how to decode circuits that can be specified using that framework. So for stabilizer circuits, we have errors, like poly errors, that can occur in the circuit. And these would be detected by certain measurement outcomes. And a data structure that we can use to capture this problem is that of a decoding hypergraph. So we would have detectors, which are products of some measurements. So these detectors would be the vertices of the hypergraph, and the errors would be the hyperedges that connect whatever polynoise with the detectors that would be triggered when this noise happens. And then finding the minimum weight error would be some kind of a hypergraph matching problem. So the way that we imagine decoding erasure circuits is to actually convert it into a stabilizer circuit. So we prove a theorem that says that if we have any pattern of erasure check detection events, we can always map it to a stabilizer circuit in that there's an equivalent stabilizer circuit with independent poly error mechanisms. And by equivalent, I mean that the distribution of errors caused by erasures in the original circuit is exactly the same as the distribution of errors caused by the polynoise in the new stabilizer circuit. And after we do this, we could just use any method for decoding stabilizer circuits on this new circuit. And I want to emphasize that the mapping can be done exactly. So any suboptimality is actually caused by the decoder and not by the mapping itself. Okay, so how exactly does this mapping work? I'll just illustrate it with one example. So suppose that we have this erasure circuit here, and EC star is going to be an erasure check with a reset following it. So we see, we have some erasure locations and some entangling gates. The first thing that we would do is to take whatever erasure check outcome here and then calculate the posterior probabilities that the qubit got erased at location E1, E2, or E3. So this can be calculated as long as we know the erasure rate and the false positive and false negative rates. If the erasure actually happened at location E1, then when the middle qubit interacts with the top qubit through gate G1, it would cause the depolarization at location F1. And when it interacts through the bottom, with the bottom qubit, then it would depolarize it at location F2. And finally, when it gets reset, then it would turn into the maximally mixed state, so that can also be thought of as a depolarization. If instead the qubit got erased at location E2, then it would just cause the depolarizations at locations F2 and F3. And if the erasure error happened at location E3, then it would just depolarize the qubit itself at location F3. OK, so this is all good. But there's one thing, which is that one extra step of like we have to reweigh some probabilities to obtain independent error mechanisms. And the reason is that when we work with the decoding hypergraphs, we assume that all of the different error mechanisms are independent. And here we have a probability distribution for the erasure happening at locations E1, E2, or E3, and these would be disjoint events. But in order to convert to independent events, it would just involve some reweighing of probability so that, for example, E1 and E2 could both happen. So if we do all of this, then we will get a stabilizer circuit that's exactly equivalent to the original erasure circuit. I'll mention that there's one more optional thing that we could do, which is to remove some correlations in the errors. And what I mean is that if the qubit was erased at location E1, then it's causing some depolarizations at at all of the locations F1, F2, and F3, and that would be like a very large correlated error. So especially when we have resets very infrequently, then we would have very large correlations, and that could make it a bit unwieldy for the decoder. So we could, for example, just calculate what is the marginal probability of depolarization at F1 and the marginal probability at F2, and just kind of feed that error model into our decoder instead. And we find empirically that this actually works quite well. OK, so now I can tell you about some of our numerical results. And the first one that we did was for the surface code. And the main question here that we wanted to address is we want to have a lot of erasure checks so that we have more precise information about where the erasures occurred. But at the same time, if you do too many erasure checks, then you're introducing more noise into the system. So kind of like what is the right balance of the frequency to actually use? So for the surface code, again, we have data qubits in black, ancilla qubits in green. And in order to measure the stabilizers, we would use a circuit like this, where we initialize ancilla in plus, entangle the qubit with the data qubits, and then finally measure the ancilla qubit in order to infer the value of the stabilizer. So if we wanted to just perform one erasure check for this entire syndrome extraction round, we could do it at location D because the data qubits would otherwise be idling at that time, so we might as well perform the erasure check there. But this might not give us enough erasure information, so we could also consider doing 2 erasure checks per round, and then we could place another erasure check at, halfway through the circuit. Or we could do 4 erasure checks, basically doing an erasure check after every entangling operations at all the locations A, B, C, and D. So we did the simulations, and one thing that we can plot is the threshold surface. And this is a surface in the phase space like E, P, and Q. So as a reminder, E is the erasure rate, P is the poly error rate, and Q is the classical bit flip rate. And we plot the surface, which is kind of the maximum amount of error that we can tolerate. So if you're beneath the surface, that means that we can arbitrarily suppress the errors by increasing the code length. And this is just an example of the threshold surface for the 2 erasure check schedule. Another thing that we can plot is the threshold surface when we, like a cross-section of the surface, when we just fix the measurement error rate to, let's say, 0.5%. And here I have many different curves. So the blue solid curve here is for the 4 erasure check schedule. Orange is 2 erasure checks per syndrome extraction round, and green is 1 erasure check. So we see that for low erasure rate, when there's mostly poly errors, then it's going to be better to use the less frequent erasure check schedule. And when there's more erasures, then it's going to be better to use more frequent erasure checks. So maybe that's not too surprising. But one interesting thing here is that even when you have like almost no poly noise and only erasure noise, the 2 erasure check and 4 erasure checks, they're almost doing the same, which means that the 4 erasure check schedule is actually causing a lot of noise into the system. In this dashed dotted line, I'm plotting what happens when we just ignore all information about erasures. So this can kind of be interpreted as a scheme under leakage, where we don't know anything about this going out of the computational subspace, but we give some extra advantage of the scheme in that it can reset the qubits for free. Okay, so the resets are not causing more noise. And we see that even under this advantage, the erasure qubits are still winning when the erasure rate is high. And if we give the same advantage to the erasure scheme, which is that the erasure checks don't cause more noise, then we get this dashed line, which is a really big advantage for using erasure qubits. And maybe that could be done if the erasure checks could be performed at the same time as entangling gates, for example. We also plot some sub-threshold scaling of the logical error rate with distance at different error rates. So here is only erasure, so we see that the 4 erasure check schedule is doing the best. When there's only poly noise, the 1 erasure check schedule is getting the best scaling. But interestingly, when we get some reasonable erasure bias, let's say 10 times more erasures than poly noise, then it's actually best to use the 2 erasure check schedule. So the optimal schedule really depends on what the noise rate actually is. And I'll just point out that there's another independent work by Katie Chung and others that also consider imperfect erasures in the context of the surface code. OK, so now let me discuss a bit about how erasure qubits could possibly be implemented. And one thing that we considered was dual rail superconducting architectures. So in some superconducting architecture, the dominant noise source is amplitude damping, where the excited state 1 decays to the ground state 0. And what we can do is just use a very simple encoding called the dual rail encoding, where logical 0 is encoded in 2 qubits as the state 0, 1, and logical 1 is encoded as the state 1, 0. So under the amplitude damping channel, it would actually make the entire computational subspace decay to the space 0, 0, and that can subsequently be detected. So one way to detect it is to measure the physical ZZ operator. Okay, but now we can ask, okay, if the experimentalists have some way of implementing physical ZZ measurements, what else can we do with this operation? So it turns out that if we do physical ZZ between different dual rail pairs, this actually implements a logical ZZ measurement. And then we thought, OK, what codes can make use of this logical ZZ measurement? And one candidate is these flow K codes. In particular, for CSS flow K codes, it could be implemented with just, in the dual rail encoding, it can be implemented with just physical ZZ measurements, which could serve both as the erasure check and as the parity measurement at the logical level, as well as if we have access to this Hadamard gate within the dual rail subspace. So we just need to measure XX and ZZ operators. OK, so we did a similar type of analysis for flow K codes, where we found the threshold surface, assuming this native entangling measurement, as well as some cross-sections where we consider different values of Q, the measurement error rate. So again, we see that in this region here, for high erasure bias, we would have a benefit by using erasure qubits compared to a standard scheme. OK, so this takes me to the end of my talk. So to summarize, we've developed a framework for working with erasure qubits. And this is exactly like specifying how to place these erasure checks, reset locations, and how to do the simulations of erasure qubits. We've also solved the decoding problem for erasure circuits under this framework by converting it into a stabilizer circuit. And this mapping can be done either exactly or approximately. We performed some simulations of the surface code and flow K codes that confirmed that you get some benefit of using erasure qubits when there is a high erasure bias. And this formalism can be used to explore further optimizations of protocols using erasure qubits, and also explore maybe different codes using erasure qubits. So I guess to answer the question from the beginning of the talk, are erasure qubits worth it? Like, the short answer is yes. But I'll say that maybe the gain is not as dramatic as a 50% threshold. But maybe the interpretation is that when we have imperfect information about erasures, the flags are a bit blurrier. But this can still help us gain maybe a 2 or 3 times benefit compared to standard qubits. And that could well be worth it in the near term when we're sitting close to the error correction threshold. So thanks for your attention.
I have one comment and this question. So comment is, I think this becomes very close to GKP codes integrated with surface code, where you have to do GKP measurement every round, and then in addition you do regular stabilizer measurements as well. And so, yeah. And so, yeah. But the question is, with GKP codes, soft information that you get from this GKP, it sort of helps a lot. Have you as I understand, you just use binary information, erasure is there or not, or did you try to have some soft information as well?
I guess we're actually using the maximal amount of soft information in that we calculate exactly what is the probability of erasure happening at every single location, and then convert that to depolarizing channel, so which is weighted by what is the probability of erasure.
Right. But your measurements, when you say it's erased or not, these are 0-1 measurements.
Oh, I see. Yeah, so I guess we have this maybe more simplistic model of, like we have either erase or not erase, and we know false positive, false negative. Yeah, one can imagine, maybe some model of erasure where you get some distribution. But then, depending on whatever measurement you get, then you would also have some false positive or false negative rate at that point. But just maybe it is not like uniform, right? Like not every location you have the same false positive and false negative rate.
You can't be too specific without an actual hardware.
Yeah, that's true. But all of this can be captured in the framework. You just have to feed in the correct numbers at every location. Yeah.
Thank you for the nice talk. So I think in practice, if you wanted to enforce the dephased noise assumption, you would do it by performing measurements like erasure checks at every round. So since you're sort of saying you shouldn't do that, do you have an idea of how this stuff would change if you started allowing coherence?
You're talking about if you can have coherences between the erasure subspace and... Yeah, we haven't thought too much about it. I mean, maybe one thing is that when you actually measure the erasure check, this would already kind of start to decohere between those two subspaces. But then the question is how this kind of spreads in the middle. So we have not analyzed this kind of more coherent spread, and I'm not sure it could be done using the stabilizer framework very easily.
That's what I would expect. Yeah, okay, cool, thanks.
Thanks for your great talk. I think it's really important to generally formalize this erasure thing. But my question is for error propagation during gates, I think it's usually going to be gates not being operated, so it's going to be coherent errors. And then if you think about erasure checks, if you fail to it, it's going to be leakage. I think it's extending the previous question. And the effect of failure of an erasure check is going to be underestimated. So did you think about actually making this more physically?
Yeah, so you're asking about this model where it doesn't necessarily cause any other error on the unerased qubit, but just the gate doesn't happen. So you essentially have this Clifford error, right?
Yeah, but then you're formalizing it as substitute Pauli errors, and I'm wondering if it's a good.
Yeah, so I would say the depolarizing spread is kind of a worst case. It's a lower bound on this performance because you just lose all information about the other qubit. You could do some analysis for dephasing spread, but yeah, then there's tricks like maybe you can like polytroll the error or do some other approximations like that, which you could do for the decoding, for example. Yeah. Does that answer the question?
Yeah, like it's you said worst case, but maybe for coherent error probably, but the erasure check, I think it's gonna be very underestimating, because if you fail on erasure check, it's gonna be undetected leakage, and it's like the worst thing that can happen.
Okay, right. So in our paper, we assume some reset mechanism that is kind of like a one-way pulse. Like if you have a qubit that's erased, then it will reinitialize it as a maximally mixed state. But if you are already in the computational subspace, like it just is kind of transparent, like it doesn't do anything to the qubit. So in that sense, like it would not stay leaked for like a long time. It's just that like if you reinitialize it and you had a false negative, then you just didn't know anything, like you didn't know the erasure happened. And it would kind of be converted to like depolarizing noise, essentially.
That's great, yeah, thank you.
Thanks for the nice talk. I have a very elementary question. So can you explain the definition of erasure error? Does that mean that qubit is simply dropped out and you get it totally traced out?
Yeah, that's one way to interpret it. Another way is like if you have some computational subspace. Okay, so I guess for example, in this dual rail encoding, the computational subspace would be 0, 1, and 1, 0, but then the erasure subspace would be 0, 0. So it's like a completely orthogonal space that like the qubit can decay to.
Okay, so why do you want to restore it into a maximal mixed state if you detected it's erased?
Okay, yeah. This is also kind of for simplicity. You can imagine, probably in the experiment you would just initialize it to a fixed state, let's say the 0 state. I don't think it would make too much of a difference in the analysis, because if you initialize it as 0, then like any stabilizer involving that is just going to be like randomized anyway, right? Because you already lost the qubit from the previous step. So you might as well have just initialized it in maximally mixed state, and we do that for our analysis.
Okay, thank you.
Hi, thank you for the talk. I just wonder, when you convert the erasure circuits to stabilizer circuits, does the decoding graph from the converted stabilizer circuits, does it have better, like, let's say, graph or decoding properties than, let's say, the one without the erasure checks?
Yeah, so it's possible that you would introduce some higher weight hyperedges from the erasure. Like if, for example, like if you're not resetting very frequently, then because this erased qubit could depolarize many other qubits, now you have like a 5 qubit depolarizing channel or something, right? Then this would be an error that doesn't occur in just the stabilizer circuit. So that is possible, and that's also the reason that we have this approximate decoding method.
Okay, thank you.
Let's take one last question.
Hi, thanks for the talk. If I understand correctly, a lot of your result relies on the theorem which shows an equivalence between the erasure errors and the poly errors, right?
Mm-hmm.
So can you comment a little bit more on the structure of that, what the transformation looks like?
Like how exactly we do this mapping?
Yeah.
Yeah, so I think, I just gave one simple example here, but in general, like, you will just have, so in our model where erasures don't spread to other erasures, like erasure is just like depolarizing, then you can kind of analyze each qubit separately. And within, the world line of this qubit between two reset locations, you can always identify locations of possible erasures, and at each erasure location where that would propagate to. So based on that, like it would be some depolarizing channels that are all nested within each other, and that would always allow you to calculate like some probabilities of 1 or 2 or 3 qubit depolarizing channels. So yeah, if you want the full details, you'll have to look at the paper for how this, how exactly to calculate all these probabilities. But it just involves some, pretty basic probability like manipulations. Yeah.
Okay, time is up. So let's thank Bailey, Lucas, Chris again.